My name is William Ročkaj, and this is Quantum Computing Demystified. Welcome to my very long and boring talk, because it's just math. Seriously, it's just a ton of math. Let me quickly go through the agenda of this talk. We will start with some quick introduction, move to math prerequisites. Then I will talk a little bit about Cubeit, move to quantum logic gates. Then the main part is about Deutsch's oracle, which will be about very simple quantum algorithm. I will mention something about quantum supremacy, and we will end up with questions and answers session. But be kind. I made those slides several months ago, and today I found out that I don't really remember much of the information what is here. So we'll see. And maybe if you got some questions, just interrupt me and ask while I'm presenting. But it's going to be probably about 1 hour long talk. So if there are lots of questions, I'm not sure if that would work, but let's try it. So this whole thing about presentations at DNA Stack started in a retrospective meeting when we found out that we don't really know each other personally, only due to work-related stuff. But I don't think anyone had a slide about them before. So yeah, I will start this new tradition. Long time ago, I had been working at Red Hat, as many other folks here, for 7 years. I started as a QA engineer, then moved to normal software development. After that, I had been working at DNA Stack for 4 years and left a lot of legacy code there. I don't envy anyone picking the code after me. Poor header. And you may be wondering what's my next step is going to be. And I'm going to start working at Exponea starting October 1st. I got a PhD in artificial intelligence. My thesis was about automatic discovery of concepts in documents written in natural language. It's a long title. That means it was a pretty good thesis, right? I had been an avid musician for a long time. And although I'm not really composing music anymore, some of you may know my biggest hit called Fiume. If you don't, just ask your colleague for a link. And I really like to get familiar with weird and unintuitive stuff like quantum mechanics or functional programming. In my free time, I like to watch TV series, movies, and play indie games. Yeah, for last, I don't know, 5 years, I've been watching Star Trek daily, but I've finished all Star Treks now. I need to find something new. And from the games, I mostly play Natural Selection, although I haven't played it for a while now. Cool. Introduction. So, I guess everyone in the meeting room, Heather, Milan, you are already familiar with this very simple formula. This is Schrödinger's equation. But of course, we cannot really do much with this simple formula. We need something bigger. So we will use time-dependent Schrödinger equation. But don't worry, it seems more complicated, but it really isn't. I guess that's how you imagined learning about quantum computing works, like crazy complex formulas no one understands, and you got lost at the very beginning. This is not the case with my talk. I'm going to make it as simple as possible. So, math prerequisites for this talk. Usually, when you start learning about quantum mechanics, everything starts with complex numbers. Not here. We don't need complex numbers. We can get away without using them. But I would strongly encourage everyone not familiar with complex number and interested in the topic to get some intuition. We would definitely need to understand some matrix operations. Let's start with an easy one, which is transposition. And that's basically converting a matrix to another matrix where you take each row and convert it to a column. So, let me try this fancy. Okay, so first row becomes first column. Second row, second column. Easy. There is a special matrix called identity matrix, which is full of zeros and only has ones on the main diagonal. Again, easy. And we need to talk about matrix property called unitarity. A unitary matrix is a matrix where if you multiply the matrix with its transpose, you got identity matrix. So if you want to have an idea, these two matrices are first this is M and this is M transposed. They look the same, but if you look closer, first row is 1 0, first column is 1 0, second row is 0 minus 1, second column 0 minus 1. So indeed the second one is first one transposed. And if we multiply them, we got identity matrix. That means all zeros and ones on the diagonal. So far, everything should be easy, no questions. Oh, I like it. Maybe you don't remember how matrix multiplication works. So just very brief reminder. You take each item in the row, you multiply it with each number in the column, like this, and you make sum of them. And you put the result in a new matrix where you put it in the, since you are using first row and first column, you put it to first row and first column. For the second row and second column, second row and third column, yeah, you will use second row and third column. Again, everything should be clear. This is crazy. So someone was like, hey Doc, I heard you like matrix multiplication. So they created something called tensor product, which just put a matrix multiplication into a matrix. And this is how we depict the function. And yeah, I really don't know how to comment it because it should be self-explanatory. You take from item for each row and each column and multiply the second matrix with it, like this, and create a new big matrix. We won't be doing operations like this during the talk. We just need it for something more simpler. We will just be doing tensor product for two column matrices. So again, we'll take the first item multiply it with each item from the second column, and that's how we construct the final column. Okay. Last but not least is called addition modulo 2. Computer scientists know it as XOR. Quick reminder, if both items are the same, the result of XOR is 0. If they are different, the result is 1. Very important, if you XOR anything with 0, you got what you had in output, you got what you had on the input. And if you use only zeros and ones, if you XOR 0 with 1, you will get 1. And if you XOR 1 with 1, you will get 0. So it's basically a negation or not operation if you only got zeros and ones. Let's move on to the interesting stuff. Cubeit. What is a qubit? I think that, again, in Canada, this must be taught in elementary schools because it seems that everyone knows what qubit is, right? As Justin Trudeau once said, regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that because, as we know, things can be both particle and wave at the same time, and the uncertainty around quantum states allows us to encode more information into a much smaller computer. Easy, clear like that. So I guess we can go to our garages and build a quantum computer because now we really understand what qubit is, right? If you're anything like me and you were reading this, you had still no idea. Okay, so it can be 0 and 1 at the same time, but how can I use that? Like, I need zeros and ones. I want to do computations. I don't need it to be all the values at once. I need a single value. I need my result. So I try to come up with an analogy. Everyone knows how coin toss works. You got a coin, you flip it in the air, it lands on the ground, and you either have heads or tails as the results. So let's call it that heads and tails, those are two states that the coin could get. Each outcome has the same probability of 50%. Again, yeah, I didn't have a slide for probability, but I hope this is clear that 1/2 is 0.5, and that's 50%. The sum of probabilities must be 1. That's how nature works. If it could be only heads or tails, it couldn't be anything else. So it must sum to 100%. And again, okay, this is clear. Everybody knows how coin tossing works. But what about qubits? Let's try to talk about new concept called Cuecoin. I thought I have coined this new concept, but yeah, I googled it and I think other people are using that as well. Basically, with Cuecoin, we will have two states as well, but we will use this new notation. This is called bracket notation, and yeah, we'll just use it because it's fancier, right? again, there is 50% probability of Cuecoin ending in the heads or tails state. And the sum of probabilities must be 100%. So when we toss a coin and then we measure it, so imagine that measuring is some operation on the toss, we will get heads 50% of the time and tails 50% of the time. And this is very important because with a single normal coin, we didn't really care about the coin in the air. But with Cuecoin, it's the most important attribute. While the coin is flipping in the air, it's not in the heads or tails state. It's not neither, it's not either, it's something different. And we can try to write it like this, where the state called toss is some linear combination of the heads and tails states multiplied by probability of heads and probability of tails. And this is basically a superposition. If there are any questions, this is the right time. I would like people to understand how I mean it. Is it clear that this is superposition? Give me some feedback, guys. I'm not talking to myself, right?
Oh, people are giving thumbs ups, but I don't think you can see us.
No, yeah. I cannot see you. Okay, so I'm continuing.
Wait, Jim has a question.
My question is, what is so P heads has a numerical value, but heads also has a numerical value? I thought it was just a state. Like, what does that mean? Does that mean heads is 0? Like you arbitrarily assign a number like 0 to represent heads, 1 to represent tails or something?
You probably need to go closer to the microphone. I don't know.
Oh, I was just wondering, like, what is, like, in that expression, you're multiplying probability of heads,
yep,
which might be, say, 50%, by heads. What is the value of heads?
Yeah,
there?
This is not a mathematical formula. Okay. It's just something that shows you that it will end up on giving you heads 50% of the time and end up in tail state 50% of the time.
Okay.
So it's not really a mathematical formula right now. But this is superposition. Mind blown. Now you understand the fundamental thing in quantum mechanics. So to sum it up, with coin you got two states, which is heads and tails. With Cuecoin, again, you got heads and tails, you just write them in a fancier form. With coin, you don't really care about the toss. You don't care about coin being in the air. With Cuecoin, this is essential part, because this is where the computation happens. And if you want to know what's the result, you will have to look at the coin to get the result. And the same thing with Cuecoin, we just call it measure. So you need to do something, some operation to measure the result. Let's get back to Cubeit. So Cubeit, like Cuecoin, is a two-state quantum mechanical system. This is a qubit. This is state 0. This is state 1. Very similar to normal bit. Qubit is like bit in the air rotating with some probabilities for each state. Those are not direct probabilities, but you can get probabilities from these numbers using this formula. You take an absolute value of it and square it. Again, probabilities must sum to 1. And how would a qubit for a Cuecoin look like? Something like this. So I can get back to this fancy bracket notation. If you see something like this, it means only that that is some variable representing a column vector. Whatever. And yeah, this is important since you are taking absolute values and squaring it. Those, if you do it for 1/2, it's 1/2, but it's the same for minus. So we never know from the result what was the original state. But I don't think we will need it. It's just for curious people. And yeah, you may wonder, why do we have absolute value here since we are squaring it? So we will get rid of that minus. That's because alpha and beta, we are just using real numbers, but those could be complex numbers. You don't need to care about this. Only if you want to, study the topic more. Just be aware that those are complex numbers and this absolute value is absolutely important. Again, how do you represent 0 and 1? As I told you, this bracket notation, this is called cat, the right part. Like bracket notation is like this. Oh, that doesn't really look good. I didn't help it. Okay, left part is bra and right part is cat. So this is cat 0 and we can represent it as a column vector 0, 1. Or we can represent it in longer state. There is a 100% probability of 0 and 0 probability of 1, which is 0. Same for 1. 1 is encoded as 0, 1. Again, 0 probability for 0 state and 100 probability for 1 state. Those are, you probably know this as a one-hot representation, where you got some states. This could be whatever. Yeah, maybe I got another slide for more qubits. Yeah, here. So if you want to use more qubits, you can write it like this, and you just do tensor product on those qubits. Again, with the formula I showed you before, you will get one long vector, and this is one hot notation. So 0, 0 would be like this. 0, 1 would look like this. How many? 4. 1, 0 again. So even here you can really forget about tensor dot product and just look at it as a one hot representation. Quantum logic gates. Now we understand what qubits are. We understand what superposition is. Now we need some tools to modify them. You all know digital logic gates. For example, here we see the AND gate, where you got several inputs, but only a single output. Again, in the table, you see the values. only when both inputs or all the inputs are 1, the output is 1 as well, otherwise it's 0. It's very similar with quantum logic gates, but there are some limitations. Quantum logic gate must be a unitary matrix, which means that if you got matrix and multiply it with the transpose, it will give you identity matrix. And again, this seems like why? And when you try to Google it, you will find that because that's how nature works and stuff like that. But basically, it's because if the matrix is unitary matrix, you are sure that sum of probabilities of your result will be 1. If this doesn't apply, you can get sum of probabilities, to be more than 1 or less than 1, and that's really not how the nature works. So that's why it needs to be unitary matrix. Another very important thing is it needs to have the same number of inputs and outputs because it needs to be fully reversible. And let's have a look on basic gate called the NOT gate. NOT gate is represented by this matrix. And if you want to apply the gate on a qubit, you just multiply the qubit with the gate. So if we use this gate or matrix on an arbitrary qubit alpha beta, we see that after multiplying, their positions are swapped. No. So let me show that for 0, right? For 0, 0 is represented as 0, 1. We would get I don't need to compute it because I know the result already, but yeah, 0 times 1 is 0 plus 1 times 0 is 0. 1 times 1 is 1 plus 0 times 0 is 0. 1 plus 0, 1. So applying the X gate on the 0 state, we will get 1 state. And it works the opposite way as well. Hadamard gate is probably the most important gate of them all. And it's basically the gate which will put your state into superposition. It's represented by this crazy matrix. And if you apply it on an arbitrary state, this is what you will get. I think I got a slide for 0 and 1. Yeah. So if you apply this matrix or apply this gate on the 0 state, this is the result, what you will get. This is how the column representation looks like. This is how normal, I don't know how this notation is called, looks like. But what it means, if I write it down here, and if I write it in a longer form, it basically means that the probability for state 0 is 50%, and it's the same for 1. So once you put a qubit, 0 qubit, into Hadamard gate, it will become a superposition of both states, 0 and 1, with the same probabilities. If you apply it to 1, it looks pretty much the same, but we got minus here. which will help us in some algorithms. It's a trick, you will see later. But still, it just means that the probability will be computed like this, and again it's just 50%. So this 0 doesn't affect the resulting probability. Another important feature of the gate is that if you apply this gate twice, or I could say even times, on the same qubit, you will get the same qubit. So if I apply the Hadamard gate here again, I will get 0. And another notation, when you apply Hadamard gate on 0, since it happens really often, we use this notation for the result. When you apply the Hadamard gate for 1, we use this notation because of the minus here. Is this clear? I'm not sure if I'm not going too fast.
I think we're good.
Great. Okay. Next slide. We're getting to quantum computing. We already know something about qubits. We know about quantum gates. So what can we do with it? Let's start and end, because that's the only algorithm I got here, with so-called Deutsch's algorithm. It's the most useless algorithm ever. Usually people ask questions like, when would I use this? It's like, it really has no value and stuff like that. So let me tell you up front, it's really useless and it's only good for teaching quantum algorithms, in my opinion. And what is it all about? You got a function which can take 0 or 1, and it will return 0 or 1. And you want to know whether this function is balanced or constant. What does that mean? If function is constant, for every input it will give you the same output. If it's balanced, in general it means that it will return one value for one half of inputs, and it will return another value for the other half of the inputs. But since we are using only single input, it can only be 1 and 0. So if it's balanced, it just means that the result for 0 and 1 would not equal. I got it all in the table so we can see it more clearly. So imagine with this problem, the function can have 4 forms. It can either return 0 for anything you input. So if you put 0 here, it will return 0. If you put 1 here, again, only 0. Or it can be constant and always return 1. So again, for 0, it will give you 1. For 1, it will give you 1. It doesn't care, always 1. Balanced, it could give you the same output as is the input. So again, for 0, the output would be 0. For 1, the output would be 1. I'm using this notation only because I want it to be consistent with another one, but this just means that it's the same. When you got modulo with 0, it always stays the same. If you got it with 1, it gets flipped. So probably like this, which is the last case. If you put 0 in, you get 1 out. If you put 1 in, you get 0 out. It just flips the bit. So 4 forms of a single function. But if you want to find whether this function is constant or balanced, you need to evaluate it twice. And that is the problem. So, for example, imagine that you evaluate it first time with 0, and you will get 0 in the return. That means the function could be either constant or balanced. You don't know. You have to evaluate it with 1, and based on the result you will see whether it's constant or balanced. And it's the same if you start with 1. You will always need 2 evaluation to find out whether the function is constant or balanced. So what can we do with it? Maybe we can try to construct quantum gate, and this is a matrix which will result in constant function always returning 1, because this is 1, as we all know, right? But the problem here is it's not a unitary matrix. If we multiply this quantum gate with its transpose, we don't get a identity matrix. So we cannot really use this as a quantum gate. Okay, what else could we do? We can try to construct some circuits for balanced functions, for just getting in the output what is in the input. We just put a straight wire here that does nothing. Or we can use the X gate for, you know, the flipping one. But again, even with this approach, we would need 2 evaluations of the function to learn about whether it's constant or balanced. And if you ask me, 2 is way too much. So people were like, okay, what can we do now? Like we have tried everything and nothing works. And then Mr. David Deutsch said, I may have an idea. Maybe we can use this crazy matrix which came to me in a vision. Yeah, probably didn't came to him in a vision. He got a paper about that, and it's a pretty complicated paper. But the basic idea is that he constructed this big quantum gate which have 2 inputs, and just takes the first input and put it to the first output. And the second input, it's called control bit, I guess. And on the second output, it combines both inputs into a single value. And here he uses the function. You don't really see the function in this matrix, but it's there. You can construct 4 matrices like this for 4 functions. And that is the main idea. And I had some troubles understanding it. So let me stress that this matrix is basically the function, because it has the function in it somehow. And this is the input of the algorithm. You got this matrix and you want to know whether it's balanced or constant. Indeed, you can, for each function, you can construct a unitary matrix. And what's cool about this, you just need a single evaluation of the function to find out whether the function is constant or balanced. And how? That's what we are going to see now. this is how the circuit looks like. Beautiful. This is your last chance. After this, there is no turning back, and you will understand how quantum computing works. First phase, initialization. We got two input qubits. So here, this is the state of the whole system. Anytime something is not clear here, please interrupt me. This is the most boring part, but we are getting towards end. Second step, you flip the second bit. It was 0, you flip it, it becomes 1. This again is the state of the system. Then you put it through Hadamard gates, which basically will put the system into superposition. So if you measure the result somewhere here, you got 25% chance that it's 0, 0. You got 25% that it's 0, 1, 25% chance that it's 1, 0, and 25% probability that it's 1, 1. Now, the oracle. Maybe I can rewrite it here. 0, 0. Oh, it will stay so. 0, 0. 0, 1. 1, 0. 1, 1. This is the hardest part, I think, because you know that first qubit will stay the same. So for this pair, first qubit is 0, it will stay the same. And second qubit will follow this function. So for second qubit being 0, it's okay, I'm confused. Zero, 0, 0, 1. It seems that I got a problem here. Okay, let me try to go along. Yeah, here. Okay, I see now. This is the second part. So it becomes epsilon is 0 plus function of x is 0. And if you do anything, if you XOR anything with 0, you got that anything. So that's why it will stay F0. Yeah. It's the same here for another term. X will stay the same. And the second is 1, because epsilon is 1, plus F was 0. That's how we got the second term. X stays the same. We take it the same way. That's how we got all the terms. And now we got this evaluated part. And let's think for a moment. So what if the function is constant? That means that f for 0 would be the same as f for 1. And we can replace all f1s with f0s. That's what I did here. And then we can start factoring things out. So in front of F0 we see 0 plus 1. In front of the blue stuff we see minus 0, minus 1. That's here. One more operation like this, and we will end up with the result which looks like this. Okay, you can probably see that we have just used the Hadamard notation for this part. Again, we can do the math later if you are interested exactly how we do that. So, in case of constant function fx, this is what we will see. This is the state of the system here. You're probably getting the grasp of quantum computing now. It seems pretty complicated, but yeah, to better understand it, you probably need to do the math yourself, and then it will become clear. But let me continue. What if the function is balanced? Again, we can use the same trick. Of course, right now we cannot say that both are the same, but we know that one is the opposite of other. So we have flipped the values. Again, if we factor things out, for the blue stuff, it's here. For the rest stuff, it's here. One more factoring out, and this is the result if the function is balanced. So the hardest part is over, but all our qubits are, let's say, they are still in the air, and we need to put them to the ground and measure them. To put them to the ground, we can use another Hadamard. Wouldn't really put them to the ground. Yeah, it's not the best analogy. Whatever. The circuit has Hadamard gate here, and if you apply it to the previous state here, after applying the Hadamard gate, you will get another state and another state if the function is constant and if the function is balanced. And this is important because here comes the trick. We only had like single evaluation of the function. And you are probably wondering, where are we getting with that? Let's put those qubits on the ground. Now you see that after measurement, if you look at the state here, if the function is constant, the first qubit will always be 0. If the function is balanced, the first qubit is always 1. What was confusing for me here is that I didn't see that this is really the first qubit. Like I was like, here is something else. So let me try to expand for constant. So in this extended formula, you should see that the system can be in state 0 F0 with 50% probability, or 0 1 XOR F0 with 50% probability. So these probabilities really relate only to the second qubit, which we don't care about. we already know that if we measure first qubit, it will always be 0. If the function is constant, if it's balanced, it will always be 1. Yeah, so this was pretty confusing for me, because here you are moving the x, so that way you would expect the x to be always the same, but the trick here is that you don't do the operations only on the state 0. You are doing it in the superposition, like this is working with coins in the air, and those coins in the air, there are neither zeros or ones, neither both, neither any of them. And basically this is how it works. You construct some crazy big quantum gates and circuits, do the magic, and you get the result in the end. You can do the same for any number of inputs. This is how it would look like. There is always this one epsilon, which is a control bit, I guess, and those are inputs. So we only had single input, but you can do something like 0, 0, 1 or 0, 1, 1, you know, stuff like that. And if you wanted to find whether a function is constant or balanced with normal computer, you would need to do 2 to n minus 1 plus 1 queries, while with quantum computer you will only use single query. And that's what is called exponential speedup. Cool. Thanks for having me here. I hope you enjoyed my talk. And if there are any questions, you can try and ask me.
Amazing. Thank you.